Okay, so I just finished the lecture on characteristic polynomials. I don't have much to say here in terms of calculation than to point out that Sage can calculate characteristic polynomials. So the syntax for calculating the characteristic polynomial of a matrix is a dot characteristic underscore polynomial, open parentheses, open quote t, close parentheses. So if you input your favorite square matrix, you can use that syntax to look at the characteristic polynomial. So I'm going to get, I've input a 4x4 matrix as default here. There'll be two print statements. The first print statement will just print out the matrix so I can make sure I put it in correctly. And then the second print statement will just give me the characteristic polynomial. Let's click evaluate and see what happens. Great. So here I have my 4x4 matrix, and the characteristic polynomial is unsurprisingly a monic degree 4 polynomial. That makes sense. And so we get t to the fourth plus 20 times t cubed minus 78t squared minus 952t minus 4,872. Now remember what we said about the Vita formulas and how they tell us information about the trace and determinant of this matrix. The trace is always the negative of the t to the n minus 1 term, where n is the size of the matrix. So here, n is 4, and the coefficient in front of t cubed is 20. That tells us that the trace of this matrix is negative 20. And of course, we can verify that for ourselves here. 1 plus negative 9 is what? Negative 8. Plus negative 5 is negative 13. Plus negative 7 is negative 20. So that checks out. We also know that the constant coefficient is always negative 1 to the size of the matrix multiplied by the constant coefficient. So, sorry, the right way to say that is the determinant of the matrix is always negative 1 to the size of the matrix multiplied by the constant coefficient. Here, the size of the matrix is 4. Negative 1 to the 4 is plus 1. So this is telling us that the determinant of this matrix is negative 4,872. If we wanted to, we could add that to the list here. I'm just going to write that just for fun. So the determinant of A equals A dot dot. And then let's add a line here to make sure this all makes sense. Or actually, I don't need that. Actually, yeah. Okay, so if I click evaluate, good. So that we can see that for ourselves. I just added this line that will calculate the determinant for us, negative 4,872. That's exactly what we expected because the size of this matrix is even and its constant coefficient is negative 4,872. I could change this around. So if I wanted to, I could put in some like terrible thing, or let's just like add 2 entries each. So negative 7, 5, 1, 2, 3, 4, or let's add 1 entry. So 1, 2, 3, 4, 5. So let's make this a 5x5. So I'm just going to add 1 entry to every row, and then I'll have to add a new row. Let's just call that last row. I'm inputting 1, 2, 3, 4, 5. So I'm just changing the matrix I input, clicking evaluate, seeing what happens. So this is now a 5x5. For this 5x5 we just input, the characteristic polynomial is a monic degree 5 polynomial, unsurprising. The fact that the next term is plus 15t to the fourth tells me that the trace of this matrix is negative 15, and we can see that for ourselves by adding all the diagonal entries. And then the constant coefficient here is plus 48,888. Well, the size of this matrix is 5, and the determinant should be negative 1 to the size multiplied by the constant coefficient. So here, the determinant of this 5x5 should be negative constant coefficient, which is negative 48,888, and that's exactly what we're finding here. So that's cool. Now, remember that for any polynomial, as long as the roots are nice enough, Sage can apply an algorithm to factor the polynomial. This, of course, is not always guaranteed, but it can happen if things are nice enough. So what I've done here is I've added a second code block, which will attempt to factor the characteristic polynomial. So here, my matrix I've input is rather large. It looks like it's a 1, 2, 3, 4, 5, 6, a 7x7. So let's hope that this 7x7 matrix has nice eigenvalues. So I click evaluate, So I see that I've input some terrible 7 by 7 matrix, but as luck would have it, this characteristic polynomial factors rather nicely. It factors as t minus 5 multiplied by t plus 4 squared multiplied by t minus 9 cubed multiplied by t plus 7 cubed. So what this is telling me is that this, what did we say the size was? 3, 4, 5, 6, 7, 8. This was a 9 by 9. For this 9 by 9, the eigenvalues are 5, -4, 9, and -7. The algebraic multiplicity of 5 is 1. The algebraic multiplicity of -4 is 2. The algebraic multiplicity of 9 is 3. And the algebraic multiplicity of -7 is 3. So as long as the matrix is nice enough, meaning that it has nice eigenvalues, the characteristic polynomial will factor here. Now, I could easily derail this. I'm sure that by just changing one entry, that will derail the whole thing. So let's make that -7 like a 0 and see what happens. Okay, so it turns out making that -7 a 0 didn't make things so bad here. This still factors pretty nicely. I bet you if I make this -29 a 0, things will go bad. Okay, so we can see here that we still get a factorization, but now I have, as part of my factorization, this cubic polynomial, which Sage couldn't factor. So we're seeing that this is sort of breaking down as I'm changing numbers in here. We still do get some roots, so we see that 9 is a root with algebraic multiplicity 2, -4 is a root with algebraic multiplicity 2, and -7 is a root with algebraic multiplicity 2. But we're still missing some roots here because Sage couldn't factor the whole thing. So that's just a cool thing to see. So you should take advantage of these calculations as you're working on your problem.